Welcome back to the deep dive. So, today I want to start with a number that in literally any other context in computer science signals just absolute victory.
Mm-hmm.
And that number is 99%.
99%?
Yeah, right? So if I'm looking at my server dashboard, whether it's a web server or a database or, a standard cache layer, and I see a 99% cache hit rate, I am popping the cheap champagne.
Oh, absolutely.
I'm telling the whole engineering team to take the afternoon off because it means we are predicting the future perfectly. The system has exactly the data it needs right there in memory, ready to go.
In a standard web serving context, yes, that is the holy grail. It means you are serving traffic without ever touching the actual hard disk. It's efficiency city.
Exactly. But today we are actually talking about a paper that argues that this exact 99% hit rate is, well, it's catastrophic. It's a complete paradox.
Yeah, it's wild.
In the specific context of modern AI agents, those coding assistants and autonomous bots that everyone's trying to build right now, this perfect hit rate is effectively creating a massive traffic jam in your data center.
It's a traffic jam that is leaving the most expensive hardware on Earth. And we are talking about clusters of H100s or A100s, the stuff people are literally mortgaging their startups for. It's leaving them sitting idle for about 60% of the time.
60% idle time on a $30,000 chip. That just hurts my soul to even think about.
It should. It's a total disaster for resource utilization. And the fascinating thing here is we aren't waiting on the brain anymore. We aren't waiting on the compute to do the math.
We're waiting on the memory.
We are waiting on the memory.
Yeah.
And not just the RAM, but the actual physical cables connecting the hard drives to the GPUs.
So today we are doing a deep dive into a paper titled DualPath Breaking the Storage Bandwidth Bottleneck in Agentic LLM Inference. And this is a heavy-hitter collaboration. It's researchers from Peking University, Tsinghua University, and the engineering team over at DeepSeek.
This paper is really a masterclass in low-level systems engineering. I mean, it identifies a bottleneck that honestly didn't really exist 2 years ago because the way we use AI has fundamentally changed.
Right.
We've moved from chat to agents, and that shift completely broke the hardware architecture we build our entire data centers around.
So our mission today is to figure out why your super smart coding agent is thinking so slowly, and why the standard architecture, which is something called prefill decode disaggregation, is failing these new workloads, and then how DualPath proposes to fix it by essentially rewiring the data center through software.
And the solution they came up with is incredibly clever. It essentially involves routing data to the wrong place on purpose just to use a faster swooping lane.
It sounds like a complete hack.
Oh, it is absolutely a hack.
Yeah,
but it's a hack that utilizes physical topology.
My favorite kind. Let's get into it. I want to set the scene with the workload first, because we hear agentic workflow as a buzzword, literally constantly on LinkedIn and Twitter. But what does it physically look like to the server? How is it fundamentally different from me just asking an LLM for a cookie recipe?
Right. To understand the hardware failure, you really have to look at the software loop. So go back maybe 2 or 3 years. We had chatbots. You ask, what is the capital of France? The model receives maybe 10 tokens. It does the math. It outputs Paris. Done.
Low context, single turn. Very transactional.
Exactly. The session is over. Now look at a coding agent today. You don't ask it a trivial question. You point it at an entire GitHub repository. You say, hey, fix the race condition in the payment processing module.
Okay, and to do that, it needs to actually read the payment module and the user definitions and probably the database schema.
Right, it needs massive context. Step 1 is reading, say, 30,000 lines of code. That's your context window.
Okay, so the GPU ingests this massive block of text. This is what we call the prefill stage, right? It processes it.
Yep. It processes it and builds the key value cache, the KV cache, and then it finally generates a thought. And here is the key distinction for agents. The thought it generates is usually very short.
Right, there's an action.
Exactly. It might just be typing out Python run tests.py.
So 30,000 tokens in and maybe 10 tokens out?
Correct. Now, the agent runs that bash command in its little sandbox. It gets an error message back, something like import error module not found.
Okay, standard Tuesday for a developer.
Yeah, pretty much. So now the agent has to decide what to do next. But, and this is the fundamental thing people forget about how these models work, LLMs are stateless in their core execution. To generate the next thought, it can't just look at the error message in isolation. It needs the entire history all over again.
It needs the original 30,000 lines of code, plus the test command it just ran, plus the new error message.
Yes, it has to re-ingest the whole timeline.
But wait a second. We just processed those 30,000 lines. They are in the cache. That's the whole point of a cache. Why are we talking about hit rates?
They are in the cache. But where physically is that cache located?
Well, ideally in the high bandwidth memory, right? Yeah. In the HBM right on the GPU die.
Ideally, yes. But HBM is incredibly expensive and it's physically finite. You have maybe 80 gigabytes per GPU. If you have thousands of active agents running in a data center and each one has a massive 30,000 token context, you run out of HBM almost instantly.
Right, you can't hold thousands of users' histories in VRAM, so where do you put that cold data?
You offload it. You shove it down the PCIe bus and onto the SSDs, the local NVMe hard drives in the server rack.
Exactly.
So the data is cached, meaning we don't have to recompute all the heavy matrix multiplication, but it's cached on the physical disk. So every single time the agent wants to think again, we have to pull that massive blob of data off the disk and haul it back up to the GPU.
Okay, I see the trap here. The paper calls this the short append property, right?
Yes, the short append property. You have a massive history. You append a tiny little bit of new data, like the error message, but you still have to fetch the whole massive history to process that tiny update.
It's like, okay, let's use an analogy here to visualize the actual bottleneck. Imagine a chef in a high-end kitchen.
Okay.
The chef is the GPU. The cutting board right in front of them is the high bandwidth memory. And the raw ingredients, the onions, carrots, stock, are in a massive warehouse down the street. That warehouse is the SSD.
I like this.
So in the chatbot era, the customer orders a soup. The chef drives the truck to the warehouse. Once gets a massive load of veggies, comes back, and just cooks for an hour straight. The driving time is negligible compared to the cooking time.
Right. You have high compute density. The chef is busy chopping and sautéing and actually using their skills.
But in the agent era, it's totally different. The customer orders soup. The chef goes to the warehouse, gets the onions, comes back, chops one single onion. Then the customer says, actually add garlic.
And because the kitchen resets, because the LLM is stateless, the chef looks at the cutting board and it's been wiped clean.
Exactly.
He has to go back to the warehouse, get the onions again, and get the garlic.
He drives back, gets onion and garlic, comes back, chops them. Then the customer says, now add pepper.
Oh, no.
He has to drive all the way back to the store to get the onion, the garlic, and the pepper.
He's spending 90% of his shift driving the truck back and forth. He's not a chef anymore. He's a logistics driver.
And the road to the warehouse is the bottleneck.
Yeah.
That connection, which in our servers are the PCIe lanes connecting the SSD to the motherboard, is getting completely gridlocked.
And the paper actually mentions a metric for this called the cache compute ratio, which puts a hard number on it.
Yeah, that metric was wild.
It's a crucial metric. For the DeepSeek V3.2 model, they calculated that they need about 22 gigabytes of data fetched for every single petaflop of compute.
That is a staggering ratio. A petaflop is a quadrillion floating point operations.
Right, so to keep that compute beast fed, to keep it doing math, you need to shovel 22 gigabytes of data into its mouth every instant. If your SSD cable can only physically transfer 10 gigabytes a second, well, the petaflop beast starves. It just sits there idling.
Waiting for the truck.
Waiting for the truck.
So we have definitively established the problem here. The agents are I/O bound. They are waiting on the hard drive, not the processor. Now let's talk about why our current data centers, which again cost billions of dollars to build, are actually set up in a way that makes this specific problem worse.
Yeah, this is where we get into PD disaggregation.
Right, prefill decode disaggregation.
Right.
Which sounds like heavy jargon, but it's actually a very logical way to organize a factory line.
Break it down for us.
Well, we realized a few years ago that reading, which is the prefill stage, and writing, which is the decode stage, are two very different math problems at the hardware level.
Right.
Prefill is highly parallel. You can process all 30,000 tokens of a prompt basically at once if you have enough cores.
Right.
It's a heavy, massive burst of compute.
Right.
Unloading a massive cargo container all at once.
Exactly. Decode, however, is inherently serial. The model has to generate one token, then it uses that token to generate the next token, then the next. It's a long, thin trickle of math. You can't parallelize the future.
So the industry split the servers. We essentially created Team Prefill and Team Decode.
Right. Team Prefill are the heavy lifters. They have machines optimized for massive batches. Team Decode are the talkers. In a standard modern cluster, the prefill engine loads the massive data from the disk, does the heavy reading comprehension, and then hands that compressed state over the network to the decode engine to actually finish the sentence.
And honestly, this sounds efficient. It's specialization of labor. You tune the machines for the specific job they do.
It is efficient for chatbots. But look at what happens in the agent loop we just described with the chef. The agent is constantly rereading its own history. It is constantly triggering that heavy prefill step over and over.
So Team Prefill is getting absolutely hammered.
They are drowning. The paper shows that the storage network interface cards, the S9Cs on the prefill nodes, are sitting at 100% utilization. They are redlining, just trying to pull KV cache data off the SSDs.
And Team Decode, what are they doing during all this?
That is the tragedy of this architecture. The decode nodes also have storage cables. They are usually the exact same physical servers with the exact same hardware specs. But because the software architecture explicitly says prefill nodes load the data, the decode node's storage cables are sitting at 0% utilization.
You have got to be kidding.
0%.
So we have a massive traffic jam on the northbound lane of the highway, and the southbound lane is completely empty.
Worse than that, we paid for both highways. You don't just buy a GPU in a data center. You pay for the liquid cooling, the massive power supplies, and the high-speed networking gear. 50% of your storage bandwidth across the cluster is effectively stranded. It's just sitting there gathering dust. But the software policy forbids the system from using it.
This is exactly what drives me crazy about massive systems engineering. It is rarely that we lack the raw hardware capability. It's that we organized it poorly. We have the pipe. We just aren't pushing water through it.
And that realization is the core insight of DualPath. The researchers looked at this bottleneck and said, wait, why are we obeying this arbitrary software rule? Why does the prefill node physically have to load the data from its own drive?
But the prefill node is the one doing the heavy matrix math. It physically needs the data in its own local memory to process it right.
True, it needs the data eventually. But the decode node is sitting right there in the same rack. And more importantly, the decode node is connected to the prefill node by a completely different network.
The compute network.
Exactly, the east-west traffic.
Let's clarify that really quick for anyone not managing a data center.
Sure. So in a modern GPU cluster, you have the storage network, which we call north-south traffic. That's the GPUs talking to the SSDs. It's fast, maybe 200 gigabits if you're lucky. But the compute network, this is the InfiniBand or NVLink scale-out fabric that is designed purely for GPUs to talk to other GPUs. And it is blazing fast. We are talking 400 gigabits, 800 gigabits per second.
It's a superhighway.
It's an absolute superhighway.
So I think I see the play they are making here. DualPath essentially says prefill node, you're too busy unloading the truck. Decode node, wake up, go to the warehouse, get the onions, and then literally throw them to the prefill node via that super fast compute conveyor belt.
Precisely. That is path B.
Okay, let's trace the routes.
Path A is the old traditional way. Storage goes straight to the prefill engine.
Direct line.
Path B is the new way. Storage goes to the decode engine, which isn't doing anything anyway. Then from the decode engine, it travels over the compute network directly into the prefill engine.
See, it feels completely counterintuitive to add a hop. In any kind of networking, adding hops is usually bad. Direct is always best. You're telling me that taking a detour through my neighbor's house and jumping the fence is faster than just walking through my own front door?
Intuition definitely says no, but the actual physics of the hardware say yes.
Yeah.
Because the bottleneck isn't the distance. The bottleneck is the read speed from the SSD itself. That is the slowest part of the whole journey. The transfer speed between the GPUs that throw across a compute network is orders of magnitude faster than the read speed.
So the time it takes to throw the data over the fence is microscopic compared to the time it takes to load it out of the warehouse.
Exactly. Let's go back to your kitchen analogy. The front door of the kitchen, which is the prefill storage, is completely jammed with delivery trucks backed up down the street. The back door, which is the decode storage, is wide open. Nobody is there.
Okay.
Now, you happen to have a runner inside the building, let's call him Usain Bolt, who can sprint from the back door to the front kitchen in 1 second. The delivery truck takes 10 minutes to unload. Do you wait for the front door to slowly clear out? Or do you route trucks to the back door and have Usain Bolt sprint the ingredients over?
You obviously use both doors.
You use both doors. And that is exactly where the dual and dual path comes from. They don't just switch to the decode node. They use both paths simultaneously. They aggregate the physical bandwidth of the entire cluster.
So you are effectively turning two completely separate physical servers into one giant logical storage controller.
Yes. You are combining the storage network bandwidth of the prefill node and the decode node. You are theoretically doubling your grocery getting capacity without buying a single new piece of hardware.
Theoretically. But we all know that in practice, adding software complexity usually breaks things in weird ways. I want to look at the scoreboard before we get into the how, because if this is just a 5% efficiency gain, it is absolutely not worth the headache of rewriting the kernel drivers.
It is definitely not a 5% gain. They tested this thoroughly on DeepSeek V3, which is their massive 660 billion parameter model, and they tested it on V3.2 as well. For offline throughput, meaning big batch processing jobs, they saw a 1.87x increase.
1.87. That is nearly double the throughput. That means a massive data processing job that used to take 24 hours now takes less than 13, just by changing the software routing.
Just software, no new cables, no new SSDs. And for online serving, which means actual human users or live agents waiting for an API response, it was a 1.96x increase.
That is insane. That is the difference between a profitable AI startup and a bankrupt one. If I can serve twice the amount of users on the exact same hardware footprint, my profit margins just exploded.
It completely changes the unit economics of running agents. Right now, running autonomous agents is generally too expensive at scale because they are so slow and tie up resources. If you make them twice as fast, they suddenly become financially viable for way more tasks.
Okay, I am completely sold on the what. Now I really want to get into the how,
Yeah.
because I know you and I know how these systems work. You're going to tell me that routing storage data over the sacred compute network is incredibly dangerous.
Oh, it is incredibly dangerous. It's terrifying.
All right, because the compute network is sacred. It's for the model to actually think. It carries the gradients, the partial sums, the actual matrix math. If we clog up that superhighway with heavy grocery deliveries, doesn't the model get confused? Doesn't the whole brain basically freeze?
This is the massive yeah but of this entire paper. You are absolutely right to call that out. The compute network handles what we call collective communications in distributed ML.
Break that down.
When a massive model is running across multiple GPUs, they have to synchronize their math constantly. Operations called all reduce or all gather, these are hyper latency sensitive operations.
So they need the network to be instantly available.
Yes. Imagine the GPUs are a choir singing a very complex song. They have to stay perfectly in sync down to the microsecond. If one GPU is waiting for a timing signal from its neighbor and that wire is suddenly clogged with a massive chunk of KV cache data being delivered from the hard drive,
The singer misses their cue.
the singer misses the cue, stops singing, and the entire choir stops to wait for them. The whole inference process stalls. Your latency spikes massively.
So DualPath isn't just a dumb routing protocol. It has to be a scheduling protocol. It requires a traffic controller that is inhumanly precise to avoid those collisions.
Inhumanly precise is exactly the right phrase. The paper introduces something they call a CNIC-centric traffic manager. And it relies on the fact that the model's computation is actually quite bursty.
What do you mean bursty?
It calculates. Then it communicates.
Yeah.
Then it calculates again. There are tiny fractions of a millisecond where the network is actually quiet. DualPath weaves the massive, heavy data transfers strictly into those tiny silences between the thoughts.
It's literally playing Frogger with the data packets across the network.
High-stakes Frogger. If you get hit by a car, which in this case is a collective comm packet, the whole multi-million-dollar cluster slows down.
So how do they actually pull this off in code? You can't just use standard Linux networking tools for that kind of precision, right?
No, absolutely not. They couldn't use the operating system's TCP IP stack. They couldn't even use the standard CUDA copy commands that NVIDIA provides.
Wait, why not? CUDA is the gold standard. It's what everyone learns in their first GPU programming class. It's the bread and butter of moving data.
They profiled it. The pure overhead of CUDA, just the CPU getting involved to tell the GPU, hey, I need you to copy this memory. That transaction takes about 5 to 7 microseconds.
5 to 7 microseconds. Come on, that sounds incredibly fast to me. I blink slower than that.
It is fast for a human. But in high-performance computing, 7 microseconds is an eternity, especially when you were trying to squeeze a massive file transfer into a 50-microsecond gap in network traffic. 7 microseconds is over 10% of your entire window completely wasted just on paperwork.
Just on the CPU filling out the forms to get permission to move the data.
Exactly. It doesn't respect the traffic isolation we just talked about. The CPU scheduler works on human time, not GPU microsecond time.
So what did they actually build to replace it?
They used RDMA rights, remote direct memory access.
So wait, RDMA is usually for remote computers talking to each other, right? They're using it for the local GPU inside the same box.
Yes. This is the ultimate engineer hack that I absolutely love. They essentially trick the system. They treat the local GPU as if it were a remote endpoint on the network. They issue an RDMA write request directly to the GPU's own compute network interface card,
The CNIC.
the CNIC.
So instead of the CPU passing a note to the GPU saying, hey, please copy this data whenever you get a second, they just essentially teleport the data directly into the GPU's memory banks via the network card.
Exactly. They completely bypass the CPU and the kernel, and the administrative overhead drops from 7 microseconds down to about 1 microsecond.
That is classic engineer over-optimization, and it is beautiful. The standard driver is too slow, so I'm going to route my local traffic through the massive network stack because the hardware network stack is physically faster than the software OS. I love it.
And it works. It gives them that surgical, precise control to inject data onto the wire only when the network is completely free.
Okay, so now there is another piece of the puzzle we need to talk about. The load balancer. The scheduler itself. Because we have two distinct paths now, path A direct and path B via the decode node. How does the system actually know which one to use at any given millisecond? It can't just be a coin flip.
No, it's a dynamic algebraic formula running constantly. They calculate two specific variables in real time, TP and TC.
Okay, lay it out.
TP is the estimated time to load the data via the standard prefill path, and TC is the estimated time to load it via the decode path plus the transfer time across the compute network.
And the time isn't just about the physical cable speed, right? It depends heavily on the queue depth.
Correct. Imagine you are standing at the grocery store checkout. Look at the two lines. Line A, the prefill line, has 50 people waiting with full carts. Line B, the decode line, has 0 people in it.
So even if line B is located further away in the store, it's going to be way faster because there's literally no waiting.
Exactly. The scheduler constantly monitors the queue depth of the storage NICs. If the prefill SNIC has a massive line of requests backed up out the door, it automatically routes the next chunk of data to the decode node.
And this decision happens per user request.
It happens way faster than that. It happens per chunk of the KV cache. They literally slice a single user's request into smaller pieces.
Wow.
They might bring the first 10,000 tokens of your history through the front door and simultaneously route the next 20,000 tokens through the back door.
It's like running a local BitTorrent swarm inside your own server rack. You're just grabbing disparate pieces of the file from wherever there happens to be available physical bandwidth.
That is a brilliant comparison. It creates a global aggregated pool of storage bandwidth instead of relying on isolated little individual hardware straws.
I want to pause here, though, and really address the edge cases, because nothing in systems engineering is free. Every optimization trades something off. Where does DualPath fundamentally break down or fail?
Well, to their credit, the researchers are very honest about this in the paper. It fails specifically when the underlying premise of an agentic workload isn't met.
Okay, what does that mean in practice?
If you are doing short prompts, like standard chatbot stuff or simple text summarization, DualPath actually adds latency overhead.
Right. If I just say, hey, tell me a quick joke, I don't need the system to load 30,000 tokens of historical context.
Exactly. The context is small, and the reuse of that context is very low. In that scenario, the computational overhead of coordinating those two paths, doing the math, calculating the queues, and managing the RDMA transfer is actually greater than the time you save by splitting the load.
So the takeaway there is don't turn this feature on for your simple Q&A customer service bot. This is heavy machinery for heavy lifting.
Right. Keep it on for the simple stuff. And there's another trap, too, the working set trap. And honestly, this one is pretty nasty.
Tell me about the working set trap.
Okay, so imagine DualPath works perfectly in your cluster. You implement it, and you speed up your entire system by 2x. That theoretically means you can now process twice as many complex agents per second on the same hardware.
Sounds great. That's the whole point. We want more throughput.
Right. You want more profit. But every single one of those active agents needs to keep its context physically in memory somewhere while it's actively being processed by the system.
Oh.
If you have 100 agents active at once, you need 100 agents worth of KV cache in the system RAM. If you suddenly have 200 agents active because your I/O is so fast, you now need 200 agents worth of active memory.
Ah, I see it.
Huh?
We hit a hard physical capacity wall. We have the bandwidth to move the data faster than ever, but we literally don't have the physical DRAM chips to store all the active data that is moving around.
Precisely. The paper deeply analyzes this effect. For their DeepSeek 660 billion parameter model, as they artificially ramped up the arrival rate of agents to test the system, The working set, meaning the total active memory required at any given second, exploded. It went from 69 gigabytes to 681 gigabytes.
Yikes. So you do all this brilliant engineering to fix the bottleneck at the SSD cable, only to immediately slam face first into a hard jam capacity limit.
That is the eternal curse of systems engineering. You never actually eliminate bottlenecks. You just move them to a new, more expensive location. We fix the I/O bandwidth. Now the bottleneck is memory capacity. To solve that, you need massive distributed memory pools, maybe even swapping back to host CPU RAM, which brings its own massive slowness and latency. It honestly never ends.
Job security for infrastructure engineers, I suppose. I also read in the paper that the actual software implementation wasn't exactly a walk in the park. They explicitly mentioned integration hell.
Integration hell is putting it very lightly. They didn't build this in a vacuum. They had to build it on top of a massive stack of other highly complex custom tools.
Tools like FlashMLA, DeepGM, DeepEP.
Exactly. Those are all DeepSeek's internal, highly optimized libraries for tensor math and parallelization.
Right.
And to make DualPath work smoothly with all of them, they had to manually modify about 5,000 lines of code deep inside the lowest level kernel of the Inference engine.
And what the biggest specific headaches they mentioned was PCIe, QoS, quality of service.
We touched on this slightly with the traffic isolation Frogger analogy. The fundamental issue is that existing modern GPUs, even the ultra-fancy NVIDIA Hopper ones, don't have great hardware-level support for PCIe quality of service.
Meaning you can't just tell the physical PCIe bus, hey, give this specific math packet priority over this background storage packet.
Right. It's mostly a free-for-all at the hardware level. It's first come, first served. If you aren't incredibly careful, your heavy background data copying the lazy grocery gathering work can completely choke the physical PCIe bus right at the exact microsecond. The GPU desperately needs to send a critical synchronization signal to its neighbor.
And if that sync signal is delayed by even a fraction of a millisecond, the GPU stalls.
The GPU stalls, then the other GPUs waiting for it also stall. The whole multi-million-dollar cluster literally hiccups.
So they couldn't rely on the hardware to be smart enough to manage it. They had to manually manage those bursts in software.
Exactly. They had to meticulously build all the smarts directly into the software driver logic.
And honestly, that is the core difference between a cool theoretical research paper simulation and a real-world production system. In a simulation, you just assume bandwidth equals X. In production, you realize bandwidth equals X unless the bus is busy or the thermal throttling kicks in or a cosmic ray hits the server rack.
And that is exactly why I have so much respect for this specific paper. They didn't just simulate it, they actually deployed it at scale. They saw the cascading failures. They fixed the complex locking issues. They fought through the integration hell.
So let's zoom out a bit. We've talked extensively about the what and the how. I want to talk about the so what for our listeners. Most of the people listening to this deep dive aren't actively running a 660 billion parameter distributed model in their basement.
Probably not. Though if you are doing that, definitely invite us over to see your cooling setup.
Seriously. But the core engineering principles here seem incredibly universal for anyone dealing with high-performance distributed systems. What are the practical takeaways we can extract?
I think there is a really solid 5-step architecture fix here that applies to a vast amount of distributed systems, not just large language models.
Okay, lay it out for us. Step 1.
Step 1. You have to identify the workload shift. You absolutely have to know if your system is compute-bound or I/O-bound. The entire tech world basically assumed AI was strictly a compute-bound problem for the last decade. But with the rise of agents, it fundamentally shifted to being I/O-bound.
Right. If you are still just endlessly optimizing your matrix math, you're optimizing the completely wrong bottleneck.
Exactly. Stop buying more expensive compute GPUs if your actual problem is the cheap hard drive cable. Step 2 is audit your idle bandwidth.
This is a huge one.
Look at your system architecture diagrams. Are there physical cables or networks that are doing nothing? In the standard PD architecture, we literally saw half the storage cable sitting completely idle. That is wasted capital and wasted potential throughput.
Find the lazy resources in your cluster. If you pay Dell or NVIDIA for the hardware capability, you better find a way to use it.
Step 3. Implement dual-path or multi-path loading. Don't be afraid to route data through a neighbor node if the direct path is clogged. In modern massive networks, the horizontal east-west speed often completely outclasses the vertical north-south speed.
The long way around is often the shortest way home.
Step 4 is specifically for the hardcore systems engineers. Bypass the standard tools. Things like standard memory copies or OS-level TCP are great for general-purpose development. But if your application needs microsecond-level precision, you might have to write custom drivers to talk to the hardware directly. The CNIC-assisted RDMA was the massive unlock here.
Don't be afraid to break the abstraction layer. If the operating system is too slow, go underneath it.
And finally, step 5. Balance the load dynamically. Static, hard-coded routing is death in a modern system. You can't just write a rule that says always use path B. You need a real-time scheduler that constantly evaluates the queue depth and routes traffic on the fly.
The traffic cop actually needs to have their eyes open.
Exactly.
I really want to dig a little deeper into that step 1, the workload shift. Because I feel like a lot of enterprise companies are going to run face first into this over the next year. They built their expensive clusters optimized for a RAG retrieval augmented generation or just simple internal chat interfaces. Now the CEO wants to deploy autonomous AI agents to fully automate their code base or analyze massive legal contracts.
And they're going to immediately see their performance absolutely tank. They're going to see GPU utilization drop to 40% and completely panic, wondering why the servers they just bought are failing.
And the high-level dashboard will just say compute at 40%. And management will think, oh, great, we have plenty of room to run even more queries.
But they don't have room, because the underlying storage I/O is absolutely pegged at 100%. The dashboard might not even show storage network bandwidth on the main page. It's very often a hidden secondary metric.
That is such a critical point. If you are actively managing or monitoring any kind of AI cluster, go add storage NIC utilization to your top-level Grafana dashboard right now.
Absolutely, especially if you are using disaggregated network storage, which almost everyone is doing now to save money and improve reliability.
Let's pivot and talk about the broader future implications of this architecture. DeepSeek is obviously pushing this hardcore because they are running incredibly massive models at unprecedented scale. But do you think this specific type of optimization will actually filter down to the rest of us?
I definitely think so. As the underlying models get more mathematically efficient, like the sparse attention mechanism they introduced in V3.2, the relative cost of the I/O actually goes up.
Wait, why?
Because the compute is finishing faster. So we are going to see this dual-path concept inevitably baked into standard open-source serving libraries like VLLM or SGLang.
It seems like it has to happen. The physical hardware just isn't changing fast enough. We aren't magically getting 10x faster SSDs next year to solve this.
No, we aren't. PCIe Gen 6 and Gen 7 are coming eventually, but they are relatively incremental updates. The fundamental gap between how fast a modern GPU can crunch numbers and how fast a modern NVMe SSD can retrieve raw data is actually widening. We absolutely need complex software routing tricks like DualPath just to bridge that physical gap.
It's really interesting philosophically that the solution here is a massive injection of more complexity. Usually in elegant engineering, we strive to simplify systems, but here we are taking a simple, direct data path and making it infinitely more complex. We're splitting data chunks, routing them dynamically through neighboring servers, tracking them and reassembling them on the fly.
Complexity is simply the price of efficiency at this scale.
Yeah.
The simple way, just using the direct path, leaves 50% of your paid bandwidth sitting on the table. If you want that 50% back, you have to pay the software complexity tax.
Complexity is the price of efficiency. That honestly needs to be on a t-shirt.
I would definitely wear it.
I want to circle back to the factory analogy for a second because it honestly helps me solidify this complex routing in my head. We have the loaders, which are our prefill nodes, and the finishers, which are our decode nodes.
Right.
The loaders were completely overwhelmed bringing raw materials into the building. The finishers were just standing around waiting for something to do. We told the finishers, hey, go grab a box of raw materials.
But the finishers logically said, wait, I can't work on the raw materials. I don't have the tools.
And we said, I know you don't. Just grab the box anyway and put it on the high-speed conveyor belt, the compute network, to send it directly to the loader who can process it.
And the loader looks up and says, thanks. Now I have 2 boxes of materials arriving for every one I used to get through my own door. And suddenly the entire factory's overall output literally doubles.
And the only actual cost of this upgrade was basically installing a smart traffic light on the conveyor belt so our raw materials don't crash into the highly sensitive important shipments.
That is honestly the perfect summary of the entire paper.
There was one specific detail in the paper we kind of skimmed over earlier, and that was the specific models tested. DeepSeek V3 versus V3.2. Can you explain the sparse attention impact a bit more clearly? Why does upgrading to the newer, more efficient V3.2 actually hurt the system more?
Sure, that's a great nuance to dig into. So traditional dense attention in a model means every single token mathematically looks at every single other token in the entire history. It is extremely computationally expensive. The math scales quadratically.
Okay.
Sparse attention, which they use in newer models, means a token only does the math to look at historically important tokens. It effectively skips a massive amount of the heavy calculations.
So the GPU finishes doing the actual math significantly faster.
Much faster. But, and here is the kicker to decide which tokens are actually important or to access them when needed, you still physically need the massive KV cache data available in memory. The actual memory footprint doesn't shrink nearly as much as the compute time shrinks.
Ah, I see. So if your required compute time drops by, say, 50%, but your massive data retrieval needs only drop by maybe 10%, your overall ratio shifts dramatically.
Exactly. You are chewing through the available data so much faster. It's like eating popcorn versus a steak. If you switch from slowly chewing a dense steak to just rapidly eating handfuls of popcorn, you need the waiter to run and refill the bowl much more frequently.
And the waiter in this scenario is the SSD. And the waiter is fundamentally slow.
And he is slow. So V3.2, which is theoretically a better, faster, and more efficient model mathematically, actually puts significantly more strain on the physical I/O system than the older, heavier V3 did.
That is so incredibly counterintuitive. Imagine being the engineer. I upgraded my massive model to the highly efficient optimized version, and my entire infrastructure crashed.
Welcome to the daily reality of AI infrastructure.
It certainly keeps us employed, right?
It does. I also want to bring up the cache hit rate metric again because it ties into this. 99%. The paper explicitly mentions that in their internal traces for these coding agents, the KV cache hit rate was consistently over 95%.
Right, and this is purely because the agent is just endlessly appending a tiny bit of newly generated text to an absolutely massive historical context.
Right, and this exact short append nature is why standard traditional caching strategies, like just trying to keep absolutely everything in fast DRAM, completely failed at this scale.
Why do they fundamentally fail?
It all comes down to cost and physical limits. If you have, say, 1 million tokens of context per active agent and you were trying to serve thousands of concurrent agents, you would need literally petabytes of high-speed RAM. That is financially and physically prohibitively expensive. You fundamentally have to use cheaper SSDs.
And the exact second you resort to using SSDs, you are right back to facing the storage bottleneck.
Exactly. The mooncake architecture, which is actually another fascinating DeepSeek paper, tries to solve this by using a massive distributed DRAM pool across the cluster. But even that massive pool gets completely filled up during the intense rollout phases in reinforcement learning.
Right, because in RL training, the agent isn't just trying to blindly solve the bug once. It's actively trying 50 different complex ways to solve the bug simultaneously to mathematically learn which one is optimal.
And every single one of those 50 separate attempts has its own massive, sprawling context history. The memory usage just completely explodes exponentially.
So DualPath is really the critical bridge here that allows us to use cheap, high-capacity storage like SSDs at almost the effective speed of expensive, low-capacity storage like DRAM, simply by aggregating all the idle bandwidth across the cluster.
That's a really great way to frame it. It effectively transforms your standard array of disparate NVMe SSDs into a massive unified high-bandwidth memory tier just by maximizing the size of the virtual pipe.
We have about 10 minutes left here. I really want to spend some time digging into the CNIC-centric traffic manager. We geek out a bit on RDMA earlier, but the traffic isolation part is really crucial to understand. The paper specifically states, collective communications occur in rapid sub-millisecond bursts. How does the software driver actually detect a sub-millisecond burst in real time?
It doesn't actually detect it reactively. That would be way too slow. It inherently knows the model architecture. It knows for a fact that layer 1 computation is always immediately followed by an all-to-all network communication. It knows exactly how many microseconds that layer 1 math will take on that specific GPU.
Oh, so it's entirely predictive. It runs on a strict schedule.
Yes, it operates on what they call a compute quota. It explicitly knows I have exactly 500 microseconds of pure computation time right now before the compute network is required by the model. So it precisely schedules exactly 480 microseconds of background data transfer.
It just perfectly fills the empty gap.
And if a massive storage request comes in, that would take, say, 600 microseconds to fully transfer. It doesn't force it. It mathematically splits it. It sends the first chunk pauses, waits for the critical model synchronization to happen, and then immediately sends the rest.
That requires incredibly precise timing at the hardware level.
It absolutely has to be precise. If the background transfer overruns its window by even 20 microseconds, it directly steps on the model's toes and cluster latency spikes dramatically.
And this is exactly why they couldn't just use the standard Linux OS scheduler. The OS scheduler basically wakes up whenever it feels like and says, oh, maybe I'll run this background thread now.
Exactly. Standard Linux is not a real-time operating system in that strict microsecond sense. They had to completely bypass the standard kernel scheduling just to achieve this level of deterministic hardware timing.
It's honestly amazing how much of cutting-edge AI system design is really just violently fighting against the operating system.
Or fighting the physical limits of the PCIe bus. At this level, it's all just hyper-advanced resource contention management.
So DualPath, it's live. It is actively running in production at DeepSeek right now. It's giving them a massive 2x boost in serving throughput. What is the next bottleneck? Once we fully solve the storage I/O and we somehow solve the memory capacity limits, what fundamentally breaks next?
The paper actually hints at this heavily in the discussion section. If we magically fix all the prefill loading limits, eventually the actual decode phase becomes the primary bottleneck again. Or the specific KV cache transfer between the prefill engine and the decode engine becomes the hard limit.
Right, because after the massive prefill engine is done doing the reading comprehension, it has to physically send that new state over to the decode engine to start talking.
Exactly. And that critical state transfer also happens over the exact same compute network. So now you have massive storage data and critical handoff data and hypersensitive model sync data all aggressively fighting for the exact same physical cables.
So we're just going to immediately need even faster physical networks.
We always need faster networks. 400 gigabit is pretty standard now. 800 gigabit is actively rolling out. We are looking at 1.6 terabit Ethernet on the horizon. And the moment it's installed, we will instantly use every single bit of it.
It's a perfect example of the Jevons paradox. The more efficient we make the data transfer, the more data we will inherently transfer.
Precisely. If we make these coding agents twice as fast, developers won't just say, great, my daily job is done faster. They will say, great, I'll just run 10 times as many autonomous agents simultaneously.
Right. Instead of having the agent fix this one tiny bug, go ahead and have it refactor the entire legacy code base.
And suddenly we are right back to square one with completely maxed out clusters.
Before we wrap up, I really want to ask you, what was your personal favorite aha moment when reading this paper? The specific technical detail that made you smile?
For me, it was definitely the loopback realization. When they deeply analyzed the prefill node's C&IC bandwidth, they realized that reading massive data from the network doesn't actually block the physical ability to write data to the network simultaneously, because PCIe lanes are full duplex. But the bottleneck wasn't the cable itself. It was the physical PCIe switch deeply embedded inside the GPU node structure. Just the sheer level of forensic hardware analysis they did, they literally tracked the electrons through the internal switches.
It really shows that you absolutely cannot treat modern hardware as a black box anymore. You have to intimately know the exact physical topology of your motherboard.
You really do. Software-defined infrastructure is honestly a bit of a lie at this scale. The harsh physical reality of the hardware always wins out.
My personal favorite moment was definitely the whole command discussion. Just the fact that CUDA-MENSTPy, the basic function we have all confidently typed 1,000 times, is essentially the villain of the story. It's like finding out that Trusted Family Butler actually did it.
The trusted butler was stealing CPU cycles all along.
I've been silently slowing down your pipeline for years, sir.
It's so true, and it really opens up the terrifying question. What other seemingly standard basic library functions are currently silently killing our cluster performance without us knowing?
That is a genuinely scary thought. Maybe the standard print statement.
A print is unequivocally the enemy of speed. Never ever leave a print statement inside your production hot loop.
Very solid advice. So let's quickly summarize the core concepts for the listener who is maybe commuting or at the gym right now. If you are actively building or deploying AI agents, your true underlying bottleneck is highly likely the hard drive physical connection, not your expensive GPU compute speed.
Right.
The proposed solution here is DualPath. Actively utilize the completely idle storage connections on your decode servers to fetch the massive data and then ship it sideways across the compute network. Doing this correctly requires totally bypassing standard OS-level tools and using RDMA hardware writes directly. The end result of this hack is a nearly 2x speed up in total cluster throughput. And the big catch is you need to be an absolute wizard at microsecond traffic scheduling to avoid completely crashing your synchronous compute network.
That is a really perfect summary. And the broader underlying lesson for engineers is actively look for the idle resources in your stack. In literally any distributed system, asymmetry is an opportunity. If one specific node is sweating bullets and the exact same hardware next to it is chilling, you have an architectural software problem that you can fix.
Asymmetry is opportunity. I really like that. So to our listeners out there, we want to hear from you. Dig into your dashboards and find your absolute weirdest edge case. Where specifically does your cluster GPU utilization suddenly drop to 40%? Is it the disk I/O? Is it a CPU thermal throttle? Is it a weird network switch configuration?
Or is it a forgotten debug print statement that you left in the core loop?
Please tell us it was a print statement. We absolutely love reading those war stories. Share your worst infrastructure nightmares in the comments, and let us know what massive technical paper or specific topic we should cover next.
We read all the comments. And if you enjoyed this incredibly deep dive into the messy guts of GPU server architecture, please leave a rating and subscribe. It really helps us keep the lights on and keep the GPU spinning.
Thanks for listening to the deep dive. Until next time, keep your cache hits high and your tail latency low.
See you next time.